All right, so we're going to get started here. And I guess I would say just a few things. First, what I understand, Heather talking to her this morning, this is the first Indian Ocean sort of focused session at an OCD meeting, so that's really nice that we are sort of pulling some folks in to talk about the Indian Ocean. And there, you'll sort of see filtered into some of these talks something we're referring to the second expedition, or the IIOE-2, which is sort of a 50-year follow-on to the original Indian Ocean expedition. And so I hope in the discussion that we have in the afternoon, we'll have the opportunity to talk about that some more, in Raleigh in particular, and Mike and some of us have been involved with that, so we can sort of broadcast some of what's going on with that. So without any further ado, so Mike McPhaden's here from NOAA PMEL, going to give us an overview of Indian Ocean dynamics from the observational perspective.
Mm-hmm. Thank you, Jerry. Also, thank you for the invitation to speak today, and thank you all for welcoming a physical oceanographer into the mix of participants. I am going to talk about the physics and dynamics of the Indian Ocean and ocean-atmosphere interactions, but I'll try to make it relevant to processes that affect biogeochemistry and ecosystems. And to keep it manageable in a short period of time, I'm going to focus on the upper ocean, so no discussion of oxygen minimum zones. I'm going to focus on some aspects of the mean circulation and variability on interseasonal to interannual timescales, that is the Madden-Julian Oscillation, the monsoons, and Indian Ocean Dipole. What motivates a lot of research, physical oceanographic research, physical climate research in the Indian Ocean is the monsoon circulation, this dramatic reversal of the winds, seasonal reversal of the winds, the hemispheric shifts in precipitation, and the really pronounced effects it has on ocean circulation. There are monsoon circulations in the other ocean basins as well, but nothing really as dramatic as occurs in the Indian Ocean. This is a fascinating scientific problem, trying to understand how the monsoons work and how to predict them, but there's also a tremendous socioeconomic relevance to this, because a third of the world's population depends on monsoon rainfall for agricultural production. And so we know that too little or too much rainfall is a bad thing, but if you could predict it even a season in advance, that would be a great value to people in the region. So that's kind of the holy grail of studying the monsoons, that is, predicting them. But the monsoons are not a monolithic phenomenon. They do vary seasonally, but embedded within the monsoons is a host of phenomena that interact across the range of time and space scales, some of which are illustrated here. On longer time scales, interannual time scales, we have the Indian Ocean Dipole, which is Indian Ocean equivalent of the El Nino phenomenon in the Pacific. We have extreme events like these recently discovered Ningaloo Niños. On shorter time scales than interannual, we have intraseasonal Madden-Julian oscillations that spawned over the Indian Ocean, affect monsoon active break periods in South Asia, but they also affect cyclone formation, tropical storm formation, all three ocean basins, the onset of ENSO events, and West Coast rainfall in the U.S. There are tropical cyclones that have really serious consequences in the Indian Ocean. This is a picture of Cyclone Nargis in 2008. There are trends in the Indian Ocean. Some of the strongest trends in the world ocean are found in the Indian Ocean, and we know these are at least in part related to greenhouse gas forcing. And then cutting across all these phenomena are issues related to ocean circulation and biogeochemical cycles and ecosystems. So it's really quite a rich array of problems embedded within the overall monsoon framework. The Indian Ocean, like the Southern Ocean, for a long time was one of the least understood and observed oceans in the world. And so about 10 years or so ago, the physical oceanographic and climate community got together, Clive R. Goose, and designed a sustained ocean observing system in the Indian Ocean, which is illustrated in this cartoon, focusing mainly on in situ components to complement the constellation of Earth observing satellites for winds, rainfall, ocean color, sea level, and sea surface temperature. And it's intended to be basin scale, and all the usual suspects are here: moorings, Argo floats, drifters, XBT lines. Also, Ghost Ship is part of this observing system. And embedded within this basin scale array are regional arrays like the Australian Integrated Marine Ocean Observing System, regional Indonesian through flow arrays. And it's also intended to support process studies, a recent one being the Cindy Dynamo study along the equator to look at the onset of the Madden-Julian Oscillation. Process studies being short-term, intensive, geographically focused. And of course, there's lots of these process studies. Here's more. One that looked at dynamics of the Seychelles-Chagos thermocline ridge that I'll talk about. These are coming up during the Second International Indian Ocean Expedition. This is Eastern Equatorial Indian Ocean upwelling, years of the maritime continent. 2 underway now: Assyria in the Arabian Sea and the North Arabian Sea, Assyria in the Bay of Bengal, and then circulation in the Arabian Sea. These are ONR funded. So there's lots of activity in the Indian Ocean. And here's a picture of the status of the Global Ocean Observing System, JCOM, a part of IOC, Intergovernmental Oceanographic Commission, puts these maps together every month. This is for June of 2016, and it shows all the various platforms that are reporting data in real time. And if we just home in on the Indian Ocean, this is what the Indian Ocean looks like. You can see the moorings. These are green squares. There are Argo floats here, dark blue, drifters, light blue. You can see the XBT lines and other measurements as well. So there's actually quite a bit of activity. Although the dots are big, they cover more area than they actually do when they're making measurements. And there's even some biogeochemical Argo floats in here. There's about 20 or so, 20 to 30, supported by Australia, India, and the U.S. One of the things that we've tried to do, if I can go back for a moment here. Yes, we started out this system as primarily physical oceanographic and physical climate, but we've connected with the cyber community to try and build more biogeochemical measurements into it. I don't know that we've been completely successful in this, but there are a few small victories that we've been able to claim, and I'll illustrate some of those in a moment. This shows the chlorophyll concentrations observed from space, ocean color, and like the physical drivers of ocean variability here, chlorophyll goes through quite a dramatic seasonal cycle. This is during the northeast monsoon in February. This is during the southwest monsoon in August. And the Indian Ocean, the upwelling zones are off the equator. We've got one along the coast of Arabia and Oman, another one here in the Seychelles-Chagos thermocline ridge region, seasonal one off Java and Sumatra. And what's notable is the lack of equatorial signal in ocean color. And that, we have some ideas about why that is. And so here is a picture of net primary production from a paper by Mike Barenfeld et al. In 2006. And what's really remarkable about this is the contrast between the equatorial Atlantic and Pacific Oceans and the Indian Ocean. We know why these high productivity regions exist in the Atlantic and the Pacific. It's because of the trade wind circulation. Produces an Ekman divergence at the surface, a geostrophic convergence at depth, and an upward flux of mass that not only brings cold water to the surface, but also nutrients to stimulate the growth of one-celled organisms. In the Indian Ocean, we have, instead of easterly trade winds, we have mean westerly winds. And we should expect those to produce an Ekman convergence. Those winds also set up the sea level to the east along the coast of Indonesia, and they tilt the thermocline down. That should produce a geostrophic divergence at depth, and that circulation should be closed by downwelling. At least that's what we expect. Now, we've actually been able to measure upwelling in the Atlantic and the Pacific Oceans, and we've not been able to do that until recently in the Indian Ocean. So I want to show you the calculation of the downwelling circulation in the Indian Ocean. And so in Rama, this moored buoy array, since 2004, we've been making moored ADCP measurements in the central basin here. This is the meridional velocity. And what's remarkable about this is you can't see a mean flow in that picture. It's dominated by what's called the biweekly wave, a fluctuation that has a peak-to-peak amplitude of about 50 centimeters a second. So you need lots and lots of data to average out these energetic waves to get a picture of the mean. And here's a picture of the 10-year mean meridional velocity at this location. It's about 4 centimeters a second to the south, maximum in the thermocline. Now, we also had an ADCP array spanning the equator for 5 years, 2008 to 2013, so we could do this calculation at several sites. And that's shown here. And so the red, the color contours, this is temperature from Argo, and the meridional velocities are shown by the vectors. South is white, black is north. And up here this is the zonal winds and the meridional winds. So the zonal winds are westerly, and what that does is it produces, you can see the Ekman convergence in the surface layer. These westerly winds set up a pressure gradient. The pressure gradient is shown by these black dashed lines, px. This is calculated from Argo, and that produces the geostrophic divergence at depth. And so there's the Ekman convergence in the surface layer, geostrophic divergence at depth. And of course, that is closed by a downwelling circulation on the equator, or near the equator. And that's why we don't get productivity on the equator in the Indian Ocean like we see in the Atlantic and the Pacific. Also, I'd point out that the downwelling's actually shifted northward. It's not right on the equator, and the reason is because the winds are not purely zonal. There's a meridional component to the winds as well. There's a southerly component, and we know from simple Ekman dynamics that shifts the downwelling downwind to the north. Now, stepping back from this picture for a moment, looking at so if we just now focus on the overall structure of the velocity field, one thing you notice is the dominance of southward flow in this section. And that's very easy to understand, in fact, because the third most famous equation in physical oceanography is the Sverdrup balance, which says the meridional transport, the first is Ekman, second is geostrophic, says the meridional transport is proportional or equals the curl of the wind stress divided by beta, which is the meridional gradient of the Coriolis parameter. And here's the curl field. It's negative. It's negative because we have westerly winds near the equator and we have easterly winds further to the south. And so that produces a net southward transport across the equator. And that actually is very important from the point of view of mean meridional circulation. This is a nice little schematic of flow on the meridional plane in the Indian Ocean. And what this net southward flow across the equator does is it carries water that's been upwelled in the Arabian Sea and Oman upwelling region southward across the equator to the subtropical high region of the southern hemisphere, where it sinks and completes this loop. It's not only important from the point of view of mass transport, but from the point of view of heat transport, because the tropics are, the ocean is gaining heat, and these meridional flows are carrying it southward, where it eventually begins to cool and release heat to the atmosphere. So we can see the importance of the meridional velocity field here. Now, I want to point out that not all the water that downwells in the subtropical high region returns to the upwelling zone of the Arabian Sea. There's another cell, we call this the southern subtropical cell, and there's a portion of this water that upwells in the southern hemisphere between about 5 to 10 south, and that is in the region known as the Seychelles-Chagos thermocline ridge region. And this is again, where we see another signature of upwelling in the high chlorophyll concentrations there. This thermocline depth is only about 50 or 60 meters on average. This is for January. And it turns out that because you have all this high productivity in the Seychelles-Chagos thermocline ridge region, that's where the tuna like to go, because they're foraging on the zooplankton and the other fish that are supported by this primary production. So it's a very important region from the point of view of biogeochemistry and ecosystems and fisheries. What do we know dynamically about this region? Well, first of all, it's highly seasonally dependent. I'll show you that in a moment. These show the conditions for January, February. And in January, February, we have the northeast monsoon winds across the equator. Here's the southeast trades. These winds produce an Ekman divergence in the surface layer that lifts the thermocline up, producing a dome in the thermocline between 5 and 10 south. This is the situation when the ITCZ in February is situated south of the equator. This is a time series from the Rama array. It's just at the southern edge of that Seychelles-Chagos thermocline ridge. And what you can see, here's the nice seasonality in the winds. They're very strong during the southwest monsoon season, and they're light and variable during the early part of the year when the intertropical convergence zone is sitting over the site. Here you can see the seasonality in sea surface temperature and in thermocline depth. It's interesting that the coldest temperatures at this location occur not when the thermocline is shallowest, but when it's deepest in July, August, September. And the reason for that is that a lot of the turbulence in this region is being generated by the winds. So strong turbulence generation by the winds is highest during the southwest monsoon. And here's a heat balance that illustrates that. These are the terms in the mixed layer heat balance. Things that warm this region are advection and surface fluxes, but things that cool this region are mixing and entrainment, turbulent and mixing and entrainment from the thermocline. And that mixing is strongest in July, August, September, which leads to the coldest sea surface temperatures and the deepest mixed layer depth at a time when the thermocline is actually deep. Now, this also, this mixing is not only bringing up cold water to cool the surface, it's bringing up nutrients. And so this is probably why we see the largest abundance of phytoplankton in this region in August when the winds are strongest rather than in January, February when the thermocline is shallowest. This Seychelles-Chagos thermocline ridge region is interesting also from the point of view of intraseasonal variability. And this is a bandpass filtered 20 to 90 day time period of TMI sea surface temperatures. So this is intraseasonal time scales in the same band as the band where the Madden-Julian oscillation is very energetic. And you can see, well, here, this is along the Arabian coast and Horn of Africa. This is due to eddies there, like the Great Whirl. But this is, I'll show you, very much due to the Madden-Julian oscillation. This is a 10-year time series of TMI data, a low-pass version of that showing the mean seasonal cycle is red. And you can see superimposed on that are these high-frequency month-to-month variations in the sea surface temperature. And that's what accounts for this strip of elevated intraseasonal variability in this ridge region. Various studies have looked at the heat balance on this time scale to try and understand what are the processes that give rise to it. And these are just a couple here. And basically, what has been found is that air-sea fluxes, particularly associated with shortwave radiation, are the main driver of sea surface temperature variations in this ridge region on this time scale. But there is also a significant month-to-month variability in turbulence and vertical turbulent mixing and entrainment. So that mixing on these shorter time scales should also have a signature in ocean color and biological productivity. Unfortunately, we don't have the data in this region to see that because when these Madden-Julian oscillations are energetic, it's also very cloudy, and the ocean color, the temporal resolution of the ocean color isn't good enough to see the interseasonal variations in this region. However, one of our small successes in cyber was to put a fluorometer on a mooring not in the Seychelles-Chagos thermocline ridge region, but to the north on the equator. And this was provided by Pete Strutton of the University of Tasmania. We got about 7 months of good data out of it before it fouled. So this is a record of fluorescence in the equatorial, what we would consider to be the equatorial desert region where we don't have mean upwelling. But what you can see is remarkably, as we move into the latter part of the calendar year, this is 2010, we see these big pulses of chlorophyll. And it turns out that these are related, at least one leading hypothesis is that they're related to the Madden-Julian oscillation. And with some clever processing of the ocean color, we can sort of see it. That is the solid black line here, but it's very much muted because because cloudiness is a problem, and so we don't get the full range that we see from the in situ data. So this is a somewhat smooth version of that chlorophyll data, and this is the wind speed variations that are associated with the MJO in this region. You can see the very high correlation. So in this region where on a monthly mean, typically, or a seasonal mean, you wouldn't see much because it's a downwelling region. On these shorter time scales, it can actually be quite explosively productive. Another time scale I want to talk about is the Indian Ocean dipole. And this is an El Nino-like phenomenon in the Indian Ocean. This is the dipole in its positive phase, where you have cold water off Java and Sumatra, and usually warm water in the western basin. And you have anomalous southeasterly winds along the coasts of Java and Sumatra, and easterly winds along the equator. And so what that does, you get, because this favors upwelling, coastal and equatorial upwelling, you get these big blooms during IOD events, like in 1997, where this is the more typical situation. And again, because of this primary productivity, it affects the higher levels of the food web and the fisheries. So the fisheries, the tuna that normally sit over the Seychelles-Chagos thermocline ridge go looking for food because, I'll show you later, that productivity decreases in the Seychelles-Chagos, or we think it does during IOD events because the thermocline is deeper. So they come looking for food to the, in this region where there's lots of productivity. So ocean circulation plays an important role, at least we think so from models. And in particular, the Wirtke jets, these are these really strong flows along the equator that transport mass east and west. And during IOD events, there's an anomalous westward transport that lifts the thermocline in the eastern basin, favors upwelling of cold water, producing cool SSTs along the coast of Java and Sumatra and along the equator, and also favors the injection of nutrients into the surface layer euphotic zone to stimulate primary productivity. So we've not measured this Wirtke jet transport or these variations systematically until we initiated this sustained observing system. So here's a 10-year record. This is the zonal velocity complement to the meridional velocity I showed you earlier, and in the central basin, and you can see these stripes of red in the upper ocean. These are the Wirtke jets. They occur twice a year, once in the spring, once in the fall. Sometimes they're stronger than others. Here in 2010, sometimes they're weaker than others, like in 2006. But we can make a mean climatology from this 10-year record, and that's shown here. And this now shows the semi-annual nature of these Wirtke jets very nicely. This is the spring jet. This is the fall jet, a little bit stronger, a little bit deeper, and it lasts a little bit longer. And they're driven by semi-annual winds along the equator during the transitions between the monsoons. So that's the mean seasonal cycle. We can compute anomalies around that mean seasonal cycle, and that's shown here. And we can compare that to zonal winds in the central Indian Ocean and the Indian Ocean dipole. All three of these time series are highly correlated, particularly during the second half of the year when the Indian Ocean dipole is best developed. And two events in particular stand out. One is the positive Indian Ocean dipole event in 2006, and there was a negative Indian Ocean dipole event in 2010. We can use any one of these time series as an index to correlate against or regress against other variables to look at the basin scale evolution of IOD events, and that's what I'm doing here. This is using the transport time series at 080 east, or along this section along 80 east, regressing against sea surface temperature and wind stress on the top, surface currents from the Oscar analysis, and surface height from altimetry on the bottom. And I've done this now for the height of a positive Indian Ocean dipole event. If you flip the sign, you'd get the same pattern for the height of a negative Indian Ocean dipole event. So this is the classic signature that we expect, upwelling favorable winds along the Java-Sumatra coast, anomalous easterlies along the equator. What that does is it transports mass from east to west in this vertijet. And so we have an anomalous flow of mass towards the west. It drains the eastern basin. It produces low sea level, and in the Indian Ocean, like other tropical oceans, the system behaves like a two-layer system, which is to say a low sea level corresponds to a shallow thermocline and a high sea level corresponds to a deep thermocline. So we're basically, because of these winds, we're draining the eastern basin of mass, transporting it westward, but also off the equator, circulating around these high sea level locations. And what that does is it lifts the thermocline then, and it stimulates, through mixing, colder sea surface temperatures, and this is also where, of course, we're bringing up nutrients to stimulate the growth of phytoplankton. And we can look at how this system evolves with time, and the point is that Rossby and Kelvin waves, these are basin scale wave phenomena, are very important in the evolution of the Indian Ocean dipole, and they connect the eastern and the western part of the basin. So here's an index. We're using the transport index again as a way to regress at various lags. This is 30 days before the peak of the vertijet and 60 days after the peak of the vertijet. And what you can see, and this is in the September, October, November timeframe when the IOD is best developed, you can see the westward propagation of these cells of high sea level south of the equator and north of the equator. The one south of the equator is larger because there's a stronger wind stress curl south of the equator. Anyways, these, as the IOD develops, these Rossby waves propagate westward, and they deepen the thermocline in the Seychelles Chagos Ridge thermocline region. At the same time, they're lifting the thermocline in the east. The other thing you can notice here is that this symmetric structure in sea level evolves with time, and what you're seeing is the influence of an equatorial Kelvin wave coming into the coast of Java and reflecting back reflecting back as a boundary generated Rossby wave with off equatorial sea level anomalies. And the other thing that's noticeable in here is the coastal Kelvin wave that's generated by the equatorial Kelvin wave coming into the coast. So the east and the west are connected on this time scale. The upwelling region off Java Sumatra is what happens here is also linked to what's happening in the Seychelles Chagos thermocline ridge region. This shows for November 2006. The high sea levels here linked to the low sea levels there are associated with upwelling here and downwelling there. So productivity increases here, decreases there, and that's why the fish go east during positive IOD events. Okay, I think I'm going to, well, very quickly, the Bay of Bengal, one of the unique features of the Bay of Bengal is the very fresh layer at the surface that isolates the mixed layer from the thermocline. And that's due to heavy rainfall, but also due to riverine input. And that leads to some dramatic contrasts in the fluxes of CO2 in the northern Indian Ocean. Here in the Arabian Sea, you see this significant outgassing in the upwelling region. There's no real outgassing in the Arabian Sea. Of course, this is not a region well constrained by observations. We saw these pictures yesterday, and it tells us nothing about the variability, which we expect to be very strong. So one of the things we've done is instituted a ocean acidification and carbon measurement system on mooring at 15 North in the Bay of Bengal with the Bay of Bengal Large Marine Ecosystem Program. And this is now when we're in our third year. You see lots of variability here, and it looks like on net there's probably more outgassing than ingassing in this region. So how am I doing on time, Jerry? Okay, wrap it up. Quickly, then I'll say the future. We're looking forward to the second International Indian Ocean Expedition, which will run from 2015 to 2020. Has a lot of themes associated with it, many of which cut across the phenomena we're talking about. The other thing that we're going to be doing is we're going to assess this induced observing system or review it in 2017. And one of the things that we really want to do, which we have not been as successful as we would have liked to up to this point, is expand the multidisciplinary measurements in this system. And that's why we will have IMBER as one of the co-sponsors of this review in late 2017. And we also want to take advantage of new technologies like gliders, for example. And then finally, one of the things that's been really frustrating is we've been shut out of the Arabian Sea largely because of the piracy problem. And this is our 2016 cruise plan for Brahma, and you can see, you know, it's this is kind of off limits. We make little incursions into it, but have not been able to get a sustained system in the Arabian Sea. Of course, this is where autonomous vehicles are valuable, but there are some things you can't do without a ship. NOAA's talking about sending the Ron Brown into the Arabian Sea in 2018 to do the I-7 ghost ship line, and we'll. And the reason for this is, of course, is that piracy has collapsed. Even though Lloyd's of London has not restricted or reduced the size of what they call the exclusion zone, there is no more piracy in the Arabian Sea. So we're looking forward to having this part of the Indian Ocean to study more. So I'll end there, and thank you for your attention.
Thanks, Mike. We have time for a couple of questions. One question while we transition over to Dennis. Sir, I've got one.
I was wondering, can you comment a little bit about on the teleconnections between IoT and other modes, other ENSO modes of SAT? Are they completely independent of the other modes of growth?
I wouldn't say they're completely independent, and different modes. IOD interacts differently. Probably the most interactive mode is with ENSO. ENSO is, when there's a big ENSO event, it tends to trigger an IOD. But there's internal dynamics to the Indian Ocean atmosphere system that you can have an IOD even without an ENSO event. So, so ENSO IOD is
It seemed to have a peak for 97, 98. Was there?
There was a peak, yeah. In fact, the biggest IOD event in modern history is 97, yeah, which happened to be the biggest ENSO event, El Nino event as well.